Let's go through number 2 in more detail. The first thing we can do is redraw the objects into a single object. Essentially pretend that they're all connected together and the total mass is 6m. I'm going to call this force applied to them Fa for applied force, and that same force would be right here. Using Newton's second law, if I want to find the acceleration, it's the net force on it, which is just this applied force, over the total mass, which is 6m. So Fa divided by 6m is my acceleration. All three objects, when I go back to looking at them individually, are going to have that acceleration. If I look at them individually and I want to find out the contact force or the tension here and the contact force or the tension here, I need to draw the free body diagram for each one individually. This force, this tension force here, this is responsible for towing 2 plus 1 or 3m out of the total 6m, or half of the total mass. That means to move it with the same acceleration, you're only going to need half the force to move half the mass. We should expect to get 1/2 of the applied force as our force right here, again, because that's the portion of the mass that's moving. Applying the same logic over here, how much force is this tow, or how much mass is this towing? Well, just m out of the total of 6m. That's 1/6 of the mass, so we should expect 1/6 of our applied force in order to move 1/6 of the mass. Drawing the diagrams individually for the objects. The first object just has the towing force, or the contact force, from the 2 on the 3. The middle object, which has a mass of 2m, has a contact or towing or tension force from the 3 on the 2, and it's got a contact force from the 1 on the 2. The first object has the actual applied force and then a contact force from the 2 on the 3. This actually should say 2 on 1 over here. 2 on 1, 1 on 2. 3 on 2, 2 on 3, and this is our applied force. By Newton's third law, this force and this force are going to be the same, and this force and this force are going to be the same. They make action-reaction pairs. We know that all three objects, even when we look at them individually, are going to have our same acceleration from up here. This is our easiest starting spot because there's only one force on it. Using Newton's second law, F net equals ma. We know the net force is that contact force from the 2 on the 1, which we're interested in finding. The mass is just m, and the acceleration from before is Fa over 6m. Cancel out the m's. That contact force from the 2 on the 1 is just the applied force over 6, which is what we said we should get way back up here. Moving on to the second object, the net force, same starting point, F net equals ma. The net force is the contact force 3 on 2 minus the contact force 1 on 2. Our mass is 2m, and our acceleration, again, is Fa over 6m. This we need to find. It's new. This we already found. Over here, it's Fa over 6. So our contact force, 3 on 2, we're going to subtract off applied force over 6, and then over here, cancel your m's. You get 2Fa over 6. And I'm not going to reduce that because this lets me combine them easier. Add Fa over 6 to both sides. You get 3Fa over 6, which simplifies to just 1/2 of the applied force for that contact force 3 on 2, which if we go way back up to the top where we walk through our shortcuts, that's what we said we should get, half the force, because it's moving in total half of the overall mass. We don't really need to do anything with this because we found these forces. But if we wanted to, we could say applied minus this force, which we know is now half of the applied force because it's the same as this by Newton's third law. So the applied force minus half the applied force will get us a net total of half the applied force remaining. And that should be enough to move 3m with that acceleration. We would get 3/6 when we start combining them. This one's got a net force of 2/6. We saw that here. This is 1/2, this is 1/6, so a half minus a sixth is a third, which is the same ratio as 2/6. So 1/3 the mass, 1/3 the net force on this, and same deal here. We just have that 1/6 for the applied force. That's enough net force to cause this acceleration on an object with mass m. Do you need to do all this every time? No, you don't. You certainly can. But if you know these shortcuts and look at what portion of the mass is that force responsible for moving, just go ahead and skip right to it.